So as our final lecture video related to op-amps, let's consider how we can use what we've learned to make a simple digital analog converter. So what we want to do is we want to design a 3-bit DAC, digital analog converter, so that our input 000 results in an output of 0 volts, and our 111 results in an output of -5 volts. And so I'll mention there's a similar example in the textbook on pages 194 to 195 if you want to look into that. So before I get into the solution again, this might be a good time to pause, maybe look back through some of the videos or the lecture notes and see if you can come up with a solution by yourself. Even after you have thought about it, maybe go through this video in stages to kind of keep pace, but maybe think about each part on your own. Okay, so with that being said, we can think about what types of circuits we've seen, and we know, for instance, circuits that we just looked at, like the integrator or differentiator, don't really fit what we need here. We noticed because it's a 3-bit DAC, we're going to want 3 different inputs, and so really only one circuit we looked at allowed for up to 3 inputs, and that was our summing amplifier. So we can think about our summing amplifier and think if that's really going to be a good fit. And so if we think a little harder about what we're doing here, we're taking these 3 input bits. For instance, up here we have our 000 or our 111. We're taking those and we want to take sort of a weighted sum. We want to take the least significant bit and weigh it less than the most significant bit. So we actually talked about how our summing amplifier does just that. So our summing amplifier is going to be a good choice here. And in particular, when we're using it in this way, we can define the circuit or call the circuit a binary weighted ladder. Okay, so binary weighted ladder. And so that's just a type of summing amplifier where we're using it for this digital analog conversion. And so I'm going to draw this a little differently than we've seen before. So even though the layout looks different, the circuit itself hasn't changed at all. So I'm going to put our op-amp in here. We're going to have our non-inverting terminal connected to ground, because remember, our summing amplifier is just a special case of our inverting amplifier, which also checks out because we know that when we have this case of 111, we want our output to be negative. So we're going from positive inputs to negative. So again, that just reaffirms that the summing amp is the correct choice. So what I'm going to do is I'm going to draw sort of across the bottom here, and we're going to have our 3 inputs coming up this way. And again, that's just to sort of visualize this a little easier in terms of what we're doing. So we're going to have our 3 inputs across the top that read like a binary number. Okay, so we have V1, V2, and V3. So for instance, we could have 0, 0, 0 for those 3 inputs. And let's call these 3 resistors R1, R2, and R3. And then of course we're going to need our feedback resistor coming from our output V out to our inverting terminal. So we're going to put that in right here. And we can call that R sub F, our feedback. Okay, so this is what our circuit is going to look like. And we can say this over here on this side is going to be our most significant bit. And we can say this V3 is going to correspond to our least significant bit. Of course, we could define that differently if we wanted, but it just kind of makes more sense to have it that way because usually we're going to read our binary numbers from left to right. Okay, so first of all, what we want to do is we want to recall our general equation for our summing amp. So let me just copy that down here. So our general equation for our summing amp we had for 3 inputs, our negative V naught is equal to, and then we have RF divided by R1 times V1 plus RF divided by R2 times V2 plus RF divided by R3 times V3. And you'll notice I've just moved the negative sign to the other side of the equation compared to what we have previously in our notes. So in general, because we're talking about a digital analog converter, we know that V1, V2, and V3, so these values here, can be 0 or 1. Okay, so we're treating those just like digital values. And so a couple other things we know is we know from our knowledge of binary that 010 is equal to a 2, right? So this is equal to base 10, 2. And so what that means is we have, if we have 0, 0, 1, well that's just a base 10, 1. And if we have 1, 0, 0, then that's going to be 4 in base 10. So essentially, if we just have V3, which remember V3 is our least significant bit, so that corresponds to this top case here, then that's sort of our baseline. But then if we just have V2, then that should be twice the amount, right? So from going from here to here, that is double. Now if we look at this third case where we just have V1, if we compare that to our first case, then that should be 4 times as large as 0, 0, 1. And then we also know that when we have this 1, 1, 1 case, we know that that should result in approximately -5 volts for our output. Okay, so in general what we can write before considering this bit here, what we can write just from up here, what we can say is we know that we have negative V out, and let's say our smallest increment, so like this 1 here, is just x. So then we know this V out is going to be 4x times V1, because V1 is 4 times as powerful as V3 we can think of, plus 2x times our V2, because our V2, like we said, is 2 times what our V1 is, or sorry, our V3 is. And then finally we have just sort of what we said our baseline was, which was our V3, our least significant bit. So now what we can do is we can combine that with this information here. So we have some specific V out, and so let me label that is for the case of V out equals -5. So now if we have V out equals -5, we have negative of -5, so that's going to become a +5, and that's going to be equal to, we just have our 4x, and for the case of 1, 1, 1, of course our V1 is going to be 1, our V2 is going to be 1, and our V3 is going to be 1. So this is for input of 1, 1, 1, and output of -5. So of course what we can do here is we can just sum those. So we on the right side would have 4x plus 2x plus x. So if we solve for x, we see that x is going to be approximately 0.714. So what we can do is we can then substitute that back into our more general equation up here, and we can say that -V naught is going to be approximately equal to 2.86 V1 plus 1.43 V2 plus 0.71 V3. And so let's call this our equation 1. Okay. And so now we know, comparing this to our general equation up here, we can see we now know what these resistor ratios should be. So for instance, if we look at RF over R1, we know that the ratio of RF over R1 should be 2.86. So again, like we saw with our previous design example in another video, what we're going to have to do is just choose a value or values, and then from there use this restriction on the ratios to get our other values. So probably the best approach to do is to select RF, because we notice RF appears in all of these ratios. So let's just sort of arbitrarily choose RF to be 10K. So a lot of times with this op-amp circuits, we're going to be working with resistors in the K ohm range. Okay, so let's say we choose RF equals 10K. Well, now we can get our 3 ratios from these 3 values here. So we can say 2.86 is equal to RF divided by R1. And so that means that our R1 is going to be equal to approximately 3.5 K ohms. we can say 1.43 is equal to RF over R2. And so from that, we get that our R2 is approximately 7.0 k ohms. And then finally, we have 0.71 equals RF over R3. And from that, we get R3 is approximately 14.1 k ohms. And so with this information and our RF here, we could come back and we could update our circuit. So let's just say we want to update this. You can just write it right out on the side here. Of course, this would be like our R1 value would be our 3.5K. This would be our 7.0K. And this would be our 14.1K and RF of 10K. So that's what it would look like if we actually went to wire the circuit up. So we could double check and we could plug in values for V1, V2, and V3 and make sort of a truth table here. So let's say we do that. We have V1, V2, and V3, and that's going to give us some output V0. And of course we can figure that out by plugging into this equation 1 here. And so if we do that, we're going to have different possibilities. So we have 1, 2, 3, 4. 1, 2, 3, 4. Okay, then 1, 2, 1, 2, 1, 2, 2. Sort of a quick way to fill out a truth table here. Okay, so there's all of our possibilities. So if we plug into that equation 1, which we had previously, we see that our Vout is going to be negative, or sorry, 0 for our first entry, negative 0.71, negative 1.43, negative 2.14, negative 2.86, negative 3.57, negative 4.29, and finally negative 5.00. So we see we have equal step sizes, which we would want if we're just counting up by 1 each time. And we see that our final value is negative 5 as we initially designed for. So that was just kind of a fun little example to show how we would use this type of circuit in practice. If you have any other questions about any of our op-amp circuits or any applications, please feel free to let me know.